Hi there, my name's Ian McTavish, and this is our Motors and FRC 2024 edition training for Hoyer Robotics Team 4152. And thank you to our sponsors who have enabled us to be as successful as we have. So we're going to start off with brushless motors. So brushless motors typically have a higher speed, which is measured in revolutions per minute, RPMs, and a higher torque, which is measured in Newton meters, compared to similar sized brush motors. The reason being, brush motors, there's a physical connection every time the motor's turning. And with the brushless motor, that physical connection doesn't happen. Um, at some point, if you're in the class, you'll get a chance to see inside the motors and see how they work, which is pretty neat. So that means that for the same size motor, you typically have more power and it's faster. The other advantage with brushless motors is they have integrated encoders, and that allows us to use closed loop control, so we can set things and have things run at certain speeds and be very accurate, which is great. The CAN bus connection allows us to access data. So, for example, if the motor is stalling, the amperage will spike, so we can build logic into our program to be able to easily tell what's happening, to make sure that we don't burn out our motors. The problem is they are more expensive. But when you add motor controllers into it and encoders, um, the price is not that hugely different in that situation. So the first motor we're going to talk about is the Kraken. So the Kraken is sold by West Coast Products or Across the Road Electronics, and the links, if you go to the slideshow version, will take you directly to the page showing you them. So, and here we can see the Kraken motor curves. So it's got a 7.16 Newton meters, and so that's a really high value. It's got a lot of torque, and at 6,000 RPMs, it's a very fast motor. So this is kind of like one of a really powerful motor that we use. You can see with the shaft, it's got a spline for the shaft, and we've got a variety of mounting points that we can use with it. So I'll just put on the laser pointer so that you can see the shaft and the mounting points. And so these curves are really useful. Basically, if you look at this is the power curve. That peak is your sweet spot. So you can see here it's about 3,000 RPMs at that. Yes, it can go up to 6,000, but you'll notice that the torque goes right down to zero when it's going at full speed. So trying to run it at 3,000 RPM is kind of the sweet spot for it. And if you go across, you can see how many, there's our 7.16 Newton meters at that point. So you can kind of get an idea of how things will work. You can also see the current, and you can see the current can spike up here. So you're realistically, if you're going to be running it, you're going to be running it at a slower speed, and not have the amount of torque, just so that you don't spike the current, and have the breaker blow. So those are things that you want to consider when you're deciding if a motor is useful or not. So the Neo Vortex, this is Rev's motor that is kind of comparable. It's a little bit faster than the Kraken, but it doesn't have the same amount of torque. And again, you've got a motor curve that you can use to refer to it. The real advantage of this particular motor is that you can have the shaft go through it. That allows for it to be packaged really nicely. We used it on our intake, to be able to mount the intake really effectively for the 2024 robot. So there's some real advantages to that packaging. The Falcon motor, I believe that we won't see this for sale anymore, but we do have quite a few, because we use them on our swerve when we did swerve for the first time. So we're still in 2024. We used 4 of these for the steering of our swerve, and then we used 4 in other locations. Very strong, high quality motors, so we'll probably be using those for a few more years till we eventually can afford to replace them with Krakens or Vortexes. The Neo brushless motor. So this was the first motor that Rev Robotics put out there with Neo. We've got quite a few of these. They're great motors. The one issue that we don't like about them is the cabling. Um, Basically, you have the red, white, and black, which are fine for power, but then you have this cable which goes to an integrated encoder. And we have had incidences where that came loose in competition. So if that comes loose, then the motor doesn't work. So that is a bit of an issue. And you want to make sure that if you're putting that in, that you're hot gluing it to make sure it's really secure. And if we can use the Vortex or the Kraken, we don't have that issue. So that is our preferred way of doing it and not using the Neos other than for prototyping. Neo 550, it has the same cable issue that the Neo has. The advantage of this particular motor is it's really, really tiny. So we used it, for example, in our 2023 robot up at the top so that it was very small weight. And the packaging worked really nicely for it. Again, I'd like to avoid using it because of that cable. We're going to probably use all the ones that we have for a mini swerve project so that we'll have a mini swerve that we can practice programming with and not have to worry about the risk of that cable coming disconnected in a competition robot. Really high speed, but much smaller torque. And you want to be careful with this. It's got a very small shaft, so you want to make sure that whatever you're mounting on that, there's not going to be a lot of force on that shaft because that is a considerable weak spot compared to the much thicker shafts of other motors. Now, ideally, we will use brushless motors, but there is a place for brush motors. The biggest thing is they're typically cheaper. They're really good for prototyping. So we've got a lot of them from previous years, and it's nice because you can just stick it up, connect it to a power and boom, it runs. The biggest problem is we don't have sensors integrated into them, so that's one reason that we try not to use them on competition robots. Having said that, there are places where we could still use them where we don't need to get that feedback. So there could be a use. The sim motor, this was the workhorse for years and years. So this shaft, the 8mm shaft with the keyway, it's the same shaft that you find on the Neo motors, and the mounting pattern of the 2-inch holes. That mounting pattern you can use with the Kraken, the Vortex, the Neo. So it's kind of a standard with it, but it's very big and heavy compared to the Kraken or the Vortex, and you're just not going to get the same output, and you don't have integrated sensors. So use it for prototyping, use it for class projects, but we'll probably not use these on competition bots. Same with the mini sim, a little bit smaller than the sim motor, so a little bit faster, but not the same torque. And again, we probably won't be using any of these. Um, we we use them on side projects and things, but as they eventually wear out, then we won't be replacing them. Now, the Redline motor and the 775 Pro. These motors are they're basically the same thing. They're 775 motors. This is the AndyMark brand, and the other one is the Vex brand. I prefer the Vex one because you can get the pulley, you can get electronics already mounted on it. But again, we'll probably not be buying any more of these, but we do have quite a few in stock that are good for prototyping little projects and things. Really high speed motors, so they used to be used a lot in shooters and things. And if you put a couple of them together, they can work well. The biggest thing is you need that airflow. So when you're mounting it, that is a factor. You got to make sure that you're mounting this and have holes for the air to be able to get through. Otherwise, it'll heat up, and that's never a good situation. The bag motor, this was a fairly small little workhorse. Basically, the Neo 550 has a similar shaft and kind of replaced it. We got a few of these kicking around, but we probably won't be bothering to buy them. So there are motor tables available that you can use, and a couple key things just going to go over. We've got our stall current. So basically, if the motor stalls, this is the current that it gets to. The the beauty of a lot of the newer motors is that these stall currents mean that the breaker will pop before the motor melts, basically. So that's a bonus. Some of our older, if you look at some of our older motors, so the mini sim, for example, or the bag motor, um, 53, it might start melting before even though you have a 40 amp breaker, you could be in a situation where the motor catches fire. So the stall torque, so this is Newton meters. So Newton meters is a metric measurement. And if you think about it, how much force does it take to push an object 1 meter? So that's kind of the idea behind it. And the bigger the number, the more power it's got. The Falcon, you can see FOC. So that's if we pay for the Pro version, we can basically access this higher level. Realistically, you're never going to kind of reach that level because we're going to be limited by the 40 amp breaker that we have on it. But basically, these values, I'm going to show you in a bit how to determine them. You've got your efficiency, and so motor efficiency, it's never 100%. So never calculate going, okay, we are going to be able to produce 7.27 Newton meters. I would take 80% of that and go, okay, we can probably get 80% of 7.2 realistically. So watts is a way, basically, if you look at your amperage and your RPMs, um, you can calculate your watts. And so that power, and that kind of gives you a framework so that if you're doing it and you're gearing it, you can do a side-by-side comparison of realistically how are these going to compare against each other. And your Newton meters based on your amperage, so your KT. So motors.vex.com has a nice table. The biggest problem with this is that the data is kind of out of date. You don't see the newer motors on here. And it looks like there's going to be 2 or 3 new motors coming for 2025. So we have to rely on a lot of data that the companies themselves provide, and we're not 100% sure how accurate it is, but it's close enough to give us a ballpark thing. So what motor to use? When we're designing a mechanism, basically, let's use a Kraken. That's going to be kind of our go-to motor. It's got enough torque and enough RPM to work in almost any situation that we find ourselves in, so we can gear it appropriately based on that. We really like the wiring, so basically we can set the wiring up so it goes from the motor all the way down to the power distribution hub without any breaks, which allows us to be much more reliable. So really like it. The Vortex, there are unique situations where through the entire motor, if you put the shaft through the entire motor, that could be a really good packaging for a situation. So we want to consider that for those kind of situations. We're going to use Falcons when we want to use a Kraken, but we don't have enough and we can't afford to buy any more. So we'll use Falcons. everything else basically used for prototyping. So the Neo motors are going to be great for prototyping because we can run them from a laptop and we can see what the actual RPM is and everything. So those that's kind of what we'll use them for, and then little projects we'll use for the other situations. And the other thing is, how do we know if a motor's going to work? So the first question is the torque. So can it do the work? So if you have the torque and you can do the physics calculations, so students that are in physics, they can determine how much torque is required. If it doesn't work, well, that's where you put in gearing. And so the gearing, let's say I've got about seven Newton meters that my Kraken can produce. It's not going to work for a 14 Newton meter task. And so what I can do is I can gear it so that I've got a gear reduction of 1 to 2. And so basically that will slow my motor down by half, but it will double my torque. So now I'm dealing with 14 Newton meters. You always want to make sure that you provide more torque from the motor than what's actually required so that you've got some wiggle room. The other question is, how fast can it go? So if you've got an elevator lifting the robot, um, then you might provide enough torque that it can do it, but it's going to take 5 seconds. Um, well, knowing that, we can determine at the end game, for example, then we've got to be in place probably 10 seconds before the end. So that's really crucial. And it's finding that balance. So enough torque to make sure that you got some wiggle room, but fast enough that you'll be able to do the task quickly. The final thing is, will it blow a fuse? So is it going to provide um, enough amperage that our 40 amp fuse is going to blow? You do have a certain amount of time where you can draw more than 40 amps. So you want to calculate those so that you know you're within your safety margins. So as mentioned, you can use gearboxes to increase or decrease um, the torque, and torque and speed have an inverse relationship. So if you increase the torque, you're going to slow it down. If you decrease the torque, you're going to increase it. And Recalc is an online calculator that you can use to check if things work. So servos are a special type of motor. Basically, there's a gearing within it, and you can set it to a position and it can move to that position. We've never used them in a competition robot, but there are some cases where that could be really handy. So we want to explore that in the next year to see if it's going to be something that can be an advantage for our team. Other factors to consider, so the shaft output. So the sim motor, for example, has an 8 millimeter shaft with the keyway. So we have sim motors and Neo motors. They share the same type of shaft, so really, really useful. The Falcon and the Kraken have a spline shaft. Now, unfortunately, both of those have slightly different splines. So if I have a pulley that uses a spline shaft for a Falcon, I can't use that pulley on a Kraken. So you want to keep that kind of thing in mind. In terms of mounting space, like, what are the physical dimensions with where we're going to put it? Where do the cables come out so that we can make sure that they're not going to get sucked into a mechanism or something? So how things are mounted are really crucial. The other thing is that when things are mounted, can you put a bearing on the other end so that the motor itself isn't getting shifted and stuff. The cables, again, this is why we really like the newer motors. So Krakens and the Neo Vortex, both of those motors, the motor controller is built into the motor. So all you need to do is provide your ground and your voltage cable and your CAN bus cables. And so that makes it really easy to manage the cables for those particular motors. It's a little bit harder for the Neo and the Neo 550 because you have that encoder cable that has to go from the motor to the motor controller. And again, your different motor controllers, Falcons, Krakens, Vortexes, they have motor controllers built into them. The Falcons and the Krakens are the Talon FX motor controllers, and then the Neo Vortex has the Spark Flex motor controller, and then you have we basically use Spark Max motor controllers. And if we're doing projects, we have a whole bunch of old motor controllers, Talon SRX, Talon SRs, Victors. We got a whole bunch of old ones. And that is our summary of motors.